Hello and welcome to Math 30-1. We are currently working in Chapter 4, which is looking at combining functions together. In 4.1, we looked at how do we add, subtract, multiply, and divide two functions if we are given their graphs. 4.2 was if we're given their equations, how do we add, subtract, multiply, and divide. And for both of those, how do we figure out the domain for in each situation, and the range at times as well. 4.3, we looked at the composition of functions, and that's where one function performs something on an input, and its output becomes input for a second function. So it's more of a substitution of one function into another function. And we talked a little bit about the complexities of determining the domain of a composition of functions, and that's what 4.4 really zeroes in on. How do we figure out that domain when we have a composition of two functions? By way of review, and just to get us started, here you see two warm-up questions. So I'd like you to imagine that both for question 1 and 2, this is a composition of two functions. What might the inside function be, the g of x, as I've shown in blue, and what might the outside function be, the f of x, as I've shown in red? Why don't you pause the video and make a prediction? What might these two functions be to create that composite function? I'm going to guess that this might be the most obvious choice that would be made for question number 1, where the f of x function has an x here that's being squared, and we're going to take the g of x function and replace the x with it so that we have x minus 3. It will all be squared, multiplied by the 2, and then have 4 added. But really, there are a lot of possible answers. You may have written down something different. And so here's one other possibility where instead we could say, well, what if f of x is just x plus 4? And then when we do the substitution, this x gets replaced with all of this 2 times x minus 3 in brackets all squared. That also would work. And this may open up your imagination to all sorts of possibilities that could arise, creating a composition of functions. For number 2, here's one possibility where we could say the inside function is the 2 over x minus 3, and that would replace the x in the f of x function, and then that just gets the 4 added on the end. Second possibility for this one could look like this, and I'm guessing again this might have been the more common choice made by students. So composition of functions, one function is substituted into a second function, replacing the x values. Well, let's look at here a composition of these two functions, f of x and g of x. To begin with, I'll have you pause the video and predict what are the domains and ranges for these two functions, because those are going to be important as we get into looking at the restrictions when we do the composition. So create the domains and ranges, and then sketch graphs of these two functions. And then for number 5, I'd like you to determine the value of g of f of 3 and then f of g of 3, and then restart the video after you've done questions 3, 4, and 5. Okay, why don't you pause now to do these 3 questions. Here you can see what I have for domains and ranges in interval notation. And you can see the graphs that I've sketched as well. Just a reminder that when we're going to find the domain of this rational function, I look at this radicand, what's underneath the square root sign, and that has to be greater than or equal to 0. And so I solve that inequality to get x is greater than or equal to 1, and that's how I got the domain for f of x. For the range for this function, because the smallest that radicand can be is 0 and then it gets bigger, and because my radical has an invisible positive sign in front, I can only get positive outputs from that f of x function or a 0. So that's where we get the range 0 to infinity. And looking at the graph, we can see that clearly as well. For the g of x function, it's linear, and we can see the line on the graph. Both domain and range, x and y, can be all real numbers. So now let's have a look at question number 5. And I said from the equations of the graphs, I'm going to look at the graphs and begin with this g of f of 3. If I were to picture what's happening here using function machines, as I've used in previous lessons, what's happening is my input of 3 is going to go into the f of x function. That's going to produce some output, which is going to go into my g of x function, and then I'm going to get an output from there. So as I look at the graph, I look to see where my x value is 3, and say, well, for f of x, what's the y value? Well, there's where f of x is, so I look across and I see my y value is 2. So what's coming out of my f of x function is a 2. That 2 has to become input into my g of x function. So now that 2, I'm going to take and make that into my input. So I look to see where now my x value is 2 and what's my y value on the g of x function. Well, the g of x function is a blue graph. There's the point. So my output is a 0. And so what I've found is this g of f of 3 is equal to g of 2, which then is equal to 0. Easy enough. Let's take a look now at this next one, which is f of g of 3, and see what's going to happen. So now as we look at that composition, 3 is going to be the input, and it's going to go into our g of x function. That's going to give us some output, which will become input into the f of x function, and that's going to give me some output at the bottom. So again, I look to see here where x is 3, and I see what's the value of g of 3. Well, I look down here and I see, well, that's where my g of x function is, and so -2 is the output that I get from the g of x function, and that's going to go into my f of x function. So at this point, I'm looking at what is f of -2. So that -2 that was output now becomes input. So here I look when x is -2, what's the y value for f of x? Well, f of x doesn't start until here where x is -1, and then it goes off to the right. So f of x doesn't exist here. So we'd have to say that f of -2 is undefined, or it doesn't exist. In other words, I can't get any output here. That's not a 0, that's an empty set. Nothing's coming out. In other words, this -2 is not acceptable input for f of x, which means this +3 cannot be acceptable input for the composition of functions. So there's a value. It can go into g of x, but it can't, its output can't go into f of x. Let's just pause for a moment here and look back at what we talked about with function machines previously. So here's a composite function machine that we looked at in a previous lesson, where we had some input. Let's say I took this apple that went into this crusher, and it can crush, crush, crush. It's acceptable input, an apple can be crushed, it gives me output. But I don't just want apple sauce or apple mush, I want apple juice. So I had a second function that I could put my juice or mush into that would strain it out, and then out the bottom I would get apple juice. So an apple was in the domain for this composition of functions. What we found, though, was bricks. If I had a strong enough crusher, my bricks could go into this first g of x function, and it would give me gravel as output. But then I have a problem. This gravel that I'm getting as output from g of x can't go into my strainer and give me anything useful out. In other words, it gunks up my machine at this middle point. And so I'd have to say the bricks are not in the domain for my composition of functions because they can't make it through this point in my composition of functions. It can come in the top, g of x can take it fine, but that problem in the middle leads to a restriction on what I will put into the very top of the machine. That's what happened in this question that we just looked at. Here, we found that this 3 was fine to go into g of x, and it gave me output that was perfectly fine in terms of g of x, but that output was unacceptable. It couldn't be used in my f of x function. And so I have to take that 3 and say that is not in the domain of my composition of two functions. So what is in the domain? Well, question number 6 looks at creating an equation, but I actually want to skip past number 6 and look at question number 7 first and determine the domain of this composition of the two functions. Then we'll look back at the equation and see how sometimes the equation can help us. So when we're looking for the domain of f of g of x, we need to look at two parts. We need to look at what's the domain of g of x to begin with. And again, if I come back to this function machine, I need to look at what is acceptable input that can come in at the top of g of x. We said the bricks could go in, but they caused a problem in the middle. In a previous lesson, we looked at this frog and said, well, this frog really shouldn't go into this crusher. That's just not a right thing to do. So we would say this frog is not part of the domain because it's not because its output can't go into the strainer, but just because it's wrong for its input to go into this crusher. So when we're looking at the domain for the composition of the functions, we have to consider what's acceptable to go into g of x, and then what output from g of x is acceptable to go into f of x. Back to this question. At this point, we're looking at the frog. What's the frog? The domain of g of x. Well, for this question, we have the domain right at the top of the page here, and we said, oh, domain is all real numbers. Anything can go into that g of x function. So I'll just remind myself of that here. The domain was from negative infinity to positive infinity, any real number. On a number line, if I were to put that on, I'm saying I can have anything, any real number from left to right, forever in both directions. So that's the first thing we look at. Here's the next thing, which is a little bit tricky at times. I'm going to look at my f of x function. My domain for the f of x function was that x had to be greater than or equal to, what was it? -1. This is not a restriction on the composition of functions. What I do instead is I think, well, I'm going to have f of g of x. So I replace the x's with g of x, which means this x gets replaced with a g of x, and I say g of x has to be greater than or equal to -1. what is that saying? Again, I'm going to come to this function machine. There's g of x. There's f of x. At this point, I'm saying my input is greater than or equal to -1, which means here my output from g of x has to be greater than or equal to -1 as well. So if that's true about my output, I need to work backwards here and say, oh, what x values here are going to give me acceptable output values for that middle part. So what I do is I take my g of x function, which was equal to -2x plus 4, and say that has to be greater than or equal to -1. Let me take this, whoops, and move it to the side over here. Now I can come and solve this inequality. So -2x will be greater than or equal to, subtract 4 on both sides, -5. Dividing by -2, remember for an inequality, when I divide by a negative, that inequality switches directions. So it becomes a less than or equal to. So x is less than or equal to +5/2. So this restriction, if I'm to put it on a number line up here, says at this point, and I'll put it on there as well, I have 5/2. Halves. There we go. And my x value has to be equal to this or less than. The domain for the composition of functions is the combination or the overlap of these two domains. Where are both of them true? And since for the g of x function we could have any real number, our final answer is going to be our domain for this composition of two functions is that x has to be less than or equal to 5/2. So that will be the domain of f of g of x. Let's look back at the graph. As we look at this graph, remember we said that my g of x function had to be greater than -1. G of x is a y value. So here's where I have y equaling -1. I'll just move this out of the way. And when I look at my g of x function, well, here g of x is equal to -1. And here g of x is 0. There g of x is 1. G of x is 2, is 3, is 4, and so on. How do I get those? Well, I look at this x value here, and I can take any x value less than or equal to that number. What is this number? 5/2. Let's come down and look at this equation now. I want to find f of g of x. I'll just pull this out from the side. My f of x function was the square root of x plus 1. Wherever I used to have an x, I substitute in the g of x, which is -2x plus 4. And then as I simplify that equation, I just get the square root of -2x plus 5. As I mentioned earlier, sometimes the equation is going to give us enough information to figure out the domain for the composition of functions, because this -2x plus 5 has to be greater than or equal to 0 because I can't square root a negative number. rearranging. Negative 2x is greater than or equal to negative 5, and just like we found below, x is less than or equal to 5 halves. So this is a situation where the equation for the composition of functions would have told us the domain for the composition of functions. But that's not always the case. So don't depend on it. Better to do what we did in number 7 to figure out the domain. If you need, pause the video at this point, kind of take some time to look back to solidify these ideas for yourself, and then you can restart it as we continue on to another example. Well, first to summarize what we put earlier or talked about, the output of g of x, if that's f of g of x, the output of g of x must be limited to acceptable input of f of x. So we adjust the domain of g of x to give that acceptable output. So in that previous question, we forced g of x to have a restricted domain where x was less than or equal to 5 halves in order to get output that was greater or equal to negative 1. All right, on to question number 8. As with the previous question, I'd encourage you to pause the video at this point and figure out domains and ranges for f of x and g of x, graph the two functions, and then determine the value of f of g of 4 and g of f of 4. So pause the video now and work your way through these 3 questions, please. Here's what I got from my domains and ranges, and you can see what the 2 graphs will look like. So the domains and ranges you may have gotten from the equations or from the graphs. G of x was probably not too bad, a little more familiar, a bit of a simpler function. F of x may have been a bit of a challenge. So let me back up for a little bit and talk about how we would figure out the domain for that function and maybe even the range. If you think about the inside function that we have here, so this radicand is a quadratic, so it's a parabola, opens down with a vertex at 4. So we could sketch a graph, and in grade 11, you looked at a fair bit of graphing here. Remember that when we're going to look at this domain, we're looking at when is this 4 minus x squared greater than or equal to 0. So again, the radicand has to be greater than or equal to 0. But a quadratic inequality can be challenging. One way that you looked at solving a quadratic inequality was to look at the graph. So here's what the graph of that 4 minus x squared looks like. If it has to be greater than or equal to 0, then what we're doing is we're looking at this point, it's equal to 0. This point, it's equal to 0. And any x value in between will give us a y value that's greater than 0. So from that, we could figure out this domain here, that x is between negative 2 and positive 2. If you didn't have the graph, then last year you looked at finding the zeros and using the zeros to divide the x-axis really into intervals. So we'd have 3 intervals when x is less than negative 2, between negative 2 and positive 2, and then greater than positive 2. And you'd stick in some test point like negative 10, and then 0, and then positive 10 to see in each of those intervals you get a positive or negative y value. What we can't do in this situation is we can't just rearrange to isolate the x squared. So if I looked at 4 being greater than or equal to x squared, well, that has to be true. But what I can't do is I can't, at this point, square root both sides. Because squaring is repeated multiplication. Square rooting is repeated division. So I'm dividing by something. But remember, when I introduce the square root sign, I introduce a positive and a negative. If I square root with a positive, it means I'm dividing by a positive, which is perfectly fine. But if I square root and I'm dividing by a negative, that means I have to switch the direction of the inequality. So that leads to a bit of a mystery. Does this inequality stay as it is, or does it switch directions? So that's why we can't simply square root both sides of the inequality like this. I'm going to leave that there for now. If we come back and think about what we did in chapter 2, where we looked at the square roots of functions, we could say, oh, the square root of this function will have invariant points where y is 1 and when y is 0. And the square root of 4 is going to be 2, so that's going to be a maximum value. And my graph will curve up and then under and then kind of like this. Looking at the graph, that can help me figure out this range. I'm only going to go that far with domains and ranges on this one. From here on, I'll just have to say, well, trust me or do some review. Okay. Question number 10. Let's have a look at that. Just like on the previous page, I'm going to look at the expressions and the function machines shown here. So what we're going to do is we're going to put a 4 into the g of x function. So I look here and see at that point, my x value is 4. I'll get g of x, which is the square root of x. Oh, a little crooked, but this is the output I get, a 2. So I'm looking for what is f of 2 equal to. So that 2 that I just put up here is going to now become an input value of 2, and I look to see what's the y value I get for f of x. Well, we hit that point, so this is equal to 0. So what we found was output from g of x was a 2. That went into f of x. Output from there was a 0. Let's have a look now at g of f of 4. So what I need to do is I need to look and see again where x is equal to 4. That'll be over here. And when I plug that in, what's the y value for my f of x function? Well, there's a problem. F of x only goes as far as 2, and it started way back here at negative 2. Oh, this is positive 2. And so 4 is not acceptable input. So I'm trying to put a 4 in here, but 4 doesn't belong. It can't go into that f of x function. So if we think back to this situation, what's happening is we have this frog. It can't go into this first function, which means it's not part of the domain for that function. So again, we need to figure out what's the domain for f of g of x. Again, we have the equation, but I'm going to skip down to the domain part first. And just like before, we're going to look at the two parts. First of all, for g of x. The domain for g of x was the square root of x, right? We had that at the top of the page. And its domain was from 0 to infinity. On the number line, there's 0. So from 0 to infinity, any of those are acceptable inputs. Next, we look at the f of x function. In the domain for f of x, I'll write it as an inequality rather than the interval notation, was that x was less than or equal to positive 2, greater than or equal to negative 2. But remember, what we're actually looking at is what is f of g of x, which means my x gets replaced with a g of x, and I need to see when is g of x less than or equal to 2 and greater than or equal to negative 2. Well, g of x was the square root of x. So I'm going to break this into two separate inequalities. Here I'm going to look at this part and say that the square root of x, maybe I should put this in blue because that's my g of x function, that has to be greater than or equal to negative 2. So I just rewrote this inequality here, but I switched the directions around to keep the root x on the left. And I'm also going to look at this part of the inequality, which says that my g of x function, square root of x, has to be, oops, not greater than, it has to be less than or equal to positive 2. Both of these statements have to be true. So I'm going to put an and in between here. So let's start with this side over here. And we'll say square root of x is less than or equal to 2. Can I square both sides? What is squaring? It's repeated multiplication. My right side is positive. My left side is also positive because there's no sign in front, which means it's a positive. So when I'm multiplying the root of x by is the root of x, I'm multiplying both sides by a positive, which means the direction of the inequality does not change. So I can square the left to get x, and I can square the right to get 4. So far, if I put that on a number line, now I have a 4 here. And I'm saying that my input can equal 4 or it can be anything less. That's as far as I'm going to go for now, because I need to still look at this inequality. Well, this time I don't want to square both sides because I'm going to actually end up with extraneous values because I have this weird situation where my right side is negative, my left side is positive. There are x values that make it true, but squaring both sides is not going to make things easier here. So instead, I'm going to think, well, this side is positive. When is a positive number greater than or equal to a negative number? Always. So over here, it's almost as though we're saying that x could be any real number because there's no x value that goes into the square root of x that would make this an untrue inequality. So if x could be any real number, but x also has to be less than or equal to 4, then I have this situation that goes like that. Is that entirely true? Well, no. We could think a little bit more intelligently and say, wait a minute, x can't be any real number because I can't square root a negative. So here I could say that x could be anything greater than or equal to 0. And I'd still have a true inequality. So x could be anything equal to 0 or greater. Whether or not I recognize that, the overlap of these two inequalities is this section here. That's the overlap, which means that the domain for f of g of x the domain is going to be from 0 up to 4, including the endpoints. let's look back at the equation. And let's see if we could figure that out from the equation. There's my f of x function, the square root of 4 minus x squared. In place of the x's, I plug in the g of x function, which is the square root of x, giving me the square root of 4 minus x. I'll move this 0 and that function machine out of the way here. As I look at this, I could say, well, what are the restrictions here? My radicand, 4 minus x, has to be greater than or equal to 0, which means 4 is greater than or equal to x, or x is less than or equal to 4. So from that, I could have had these values in this direction, and then when I look to see what's the overlap of these two inequalities, again I get between 0 and 4. So another situation where the equation of the composite functions was sufficient to help me figure out the domain for that composition of functions. And I keep saying this doesn't always happen. So far it's always happened. Let's look at another example to see, is it going to happen here as well? I'll have you pause the video and work through these questions. Is it just two? Yep, just two on this page. We have this function f of x. We want to state the domain of the function and then determine the equation for f of x and figure out its domain. So why don't you pause the video here, try these two questions, and then restart the video when you're ready. Here I've got it started. So rational function, denominator can't be 0, non-permissible values when x is equal to -1. So my domain x can't equal -1. Really, when we're asked for domains, should use interval notation or full set builder notation. This is just a little cleaner to keep things from getting too confusing as I work through it. So similarly, as I have done with the previous questions, as I think about the composition of these two functions, first, I'm going to go into the f of x function. So that's going to be my inside function here. And then that output goes back into the f of x function to see what we get. So here I have this restriction. Tells me -1 cannot go into that function. And over here is where I'm looking to see, oh, what restriction do I get for that kind of joint piece where the output from the first function goes into the second function. My f of x function is x over x plus 1. That cannot equal -1. So as I go through and rearrange for this, I'll get x can't equal -x minus 1. Collecting the x's to one side, 2x can't equal -1, which means x cannot equal -1/2. So the domain for f of x is going to be from -infinity up to -1, -1 to -1/2, -1/2 to positive infinity. Ooh, I got close. I'll move this, move that. There we go. There's the domain for that composition of functions. And kind of a more clean, abbreviated way is to say x can't equal -1, x can't equal -1/2. Then when we're going to look at the equation, here we go. My f of x function is equal to x over x plus 1. Inside, I put my f of x function, which is x over x plus 1. And now we want to simplify this. So there are a couple ways to do this. The most common way that students think of at this point is to simplify the denominator and then take the reciprocal to multiply. I'm not going to do it that way because, well, partly because the method I'm going to use is less often recognized as an option by students, but also it's often a little more efficient. So what I'm going to do is I'm going to look at multiplying the numerator by x plus 1 and the denominator by x plus 1. Because that x plus 1 is what's in the denominator of fractions inside my big rational expression. So if I show more detail than many of you will need to see, I'll have x over x plus 1 in the numerator and x over x plus 1 in the denominator, and then I have a plus 1 over there. That x plus 1 from the top gets multiplied in here. In the bottom gets distributed. So it looks kind of like that. And we can see that the reason for doing this is because there I can cancel out x plus 1s. Here I can cancel out x plus 1s. And I don't have any more fractions inside of fractions. My numerator is just an x. My denominator is an x plus 1, which will simplify down to x over 2x plus 1. And this is f of x. There is my equation with my domain, which I could say x can't equal -1 or -1/2. And again, I could have gotten that -1/2 from the equation. Right? I can look at this and say, oh, 2x plus 1 can't equal 0. 2x can't equal -1. X can't equal -1/2. Mr. Wagner, how come you keep telling us that the equation's not good enough? Well, because of questions like this. Again, I'll have you pause the video, work through this one, and you'll see that the simplified equation you're going to get is not going to give you the restrictions you need. So pause the video, work through this question, restart it when you're ready to see my work. Here's my initial equation. As I did for the previous question, I'm going to multiply numerator and denominator by that common denominator of 1 minus x. And there we go. I get f of g of x is equal to x. Looks like x could be any real number. But let's back up and think about domains. For my inside function, x can't equal 1. For my outside function, f of x, the domain is x can't equal -1. But again, remember, I'm looking, you boards are doing something a little weird here. We'll see if it makes it through the end of this video. I need to replace the x with a g of x and say that g of x can't equal 1. So I can't here at this point say get a value of -1. -1 not permitted in that middle part. So I look at my g of x function, x over 1 minus x. That cannot equal -1. And as I go through to solve, x can't equal -1 plus x. Interesting. As I rearrange this, I get 0 can't equal -1. Huh. Well, when is that true? That's never true, which means that this is adding no new restrictions. So the only restriction that I have is this restriction, where x can't equal +1. So for this function, this composition of functions, I will have the restriction or the domain that x cannot equal +1. And that's it for restrictions. There's another question. G of f of x can state its domain. Pause the video and you can work through this. Restart when you're ready. Here I go. That's not what I want to do. Let's try this. Again, I can go through the steps. I can multiply numerator and denominator by that common denominator, and once again, I end up with x as the result. So g of f of x is equal to x. As I look at the f of x function, my domain is x can't equal -1. So that restriction has to carry all the way through again. So we're here right away. I'm going to say x can't equal -1. And then I'll look at my g of x function. And its domain was that x couldn't equal +1. But again, what I'm interested in is g of f of x. So f of x can't equal +1. And as I work this through, x over x plus 1 can't equal 1. I'm going to run out of space, so I'll go up over here. X can't equal x plus 1. Subtract x on both sides. 0 can't equal 1. No new restrictions. And so we have, here is our composition of functions with the restriction that has to be carried through. Notice for both of these, the input of x became the output of the composition, which is what happens when we have functions that are inverses. So when we have a situation where f of g of x equals x, and these both have to be true, g of f of x equals x, then these two functions are inverses. In other words, when I do composition of an inverse and a function, composition of a function and its inverse, and both of them equal x, they are inverses of each other. There we go. We have made it through this long, long lesson. So, do we stop here? Oh, we could, or I could say, but wait, there's more. What's the more that there could be? How could there possibly be anything more? Well, what if we had the composition of three functions? You could be asked to do some work with the composition of three functions, but I will not, on a test or quiz or on a diploma exam, ask you to figure out domains with the composition of more than two functions. So at least you don't have to worry about that, because if we did, we'd be considering, oh, what's possible input for g of x? What output from g of x is acceptable input for f of x? And then we work backwards to figure out what are the restrictions on the x. And then we'd say what output from f of g of x will give us acceptable input here. And then we'd have to work all the way back here to figure out what are the restrictions on x. Super complex. So you don't have to worry about it. Let's stop there and run away. Have a good day.